To do a multi-step calculation using proper significant figures, first do the calculation without rounding. For example, we can add 1.213 plus 2.5, then divide by 6.75, and come out with 0.550074. After doing the calculation without rounding, go through it again, but this time pay attention to proper significant figures. The first step in this problem is an addition, which gets rounded based on digits after the decimal. Our second number, 2.5, has one digit after the decimal. Therefore, we round the answer in our numerator to one digit after the decimal, making it 3.7. Once we have rounded based on our addition rule, we determine the number of significant figures in that answer, so that when we do the division, we can have proper significant figures. 3.7 has 2 sig figs, and 6.75 has 3 sig figs. So our answer gets rounded to 2 significant figures. At this point, we reference our original unrounded calculation, and we round that number to 2 significant figures. 0.550074 rounded to 2 sig figs is 0.55. An example of a multi-step calculation is one like we do in the lab. We are using Archimedes' principle to determine density of a metal bar. We are using the equation density equals mass divided by volume. Mass in this example is 69.658 grams. Volume is the difference between final volume, VF, which is 22.4, and initial volume, VI, which is 13.5. We first go through the calculations without rounding and come out with 7.8267 grams per cubic centimeter. We go through the calculation again, paying attention to significant figures. The subtraction step is based on digits after the decimal. Since 22.4 and 13.5 both have one digit after the decimal, we keep one digit after the decimal in our denominator, and the number is 8.9 milliliters. Since 1 milliliter is equal to 1 cubic centimeter, we can change the units to cubic centimeters. We want to do this because we are trying to express the mass of the metal bar, which is solid, rather than the mass of the water, which is liquid. Then we do the division step, which is based on total significant figures. The top number has 5 sig figs, the bottom has 2. So we keep 2 sig figs in our final answer. When we round 7.8267 to 2 sig figs, we come out with 7.8 grams per cubic centimeter. After carrying out the operation, parentheses 13.7 plus 0.027, parentheses, divided by 8.221, how many significant figures are appropriate to show in the result? Is it A, 1, B, 2, C, 3, D, 4, or E, 5? If we want, we can rewrite the way this problem is laid out. We can put the 13.7 plus 0.027 on the top, and then we're dividing by 8.221. So we could plug it first directly into our calculator to get an unrounded value. And we would do the addition part first, 13.7 plus 0.027. You could hit enter, and then divide by 8.221. And we would come out with an unrounded value of 1.669748, and that should give us plenty of digits to work with our rounding. We want to make sure that we do this step of getting the unrounded value first so that we can avoid rounding error. However, in order to express our answer with proper significant figures, we're going to need to go through the problem a second time, but this time rounding after each step to the appropriate significant figures. And that will help us keep track of how many sig figs we actually get to keep. So our first step is an addition step, 13.7 plus 0.027. And when we round it, it's going to be based on digits after the decimal following the addition and subtraction rule. Our first number has 1 digit after the decimal, and our second number has 3 digits after the decimal. So we're going to round our answer to 1 digit after the decimal. We actually round our answer to 13.7. Then, after we have completed the first step, which is the addition, rounding appropriately, then we can do the second step, which is the division. So we do 13.7 divided by 8.221. And we're going to round this answer to 3 significant figures because our top number, it has 3 significant figures. The bottom number has 4, which is more, but we can only go with the least significant figures following the multiplication and division rule, which goes by total significant figures. So when we round our answer to 3 significant figures, I don't actually want to bother doing this particular division and rounding this answer to 3 sig figs. Instead, I'm going to round my original unrounded value to 3 significant figures. If I were to do this one and round to 3 sig figs, I might end up with some rounding error. So I'm going to go back to my original and round that to 3 significant figures. So the 1, the 6, and the 6, we're going to keep. The 9 is important, is going to fall off, but before it does, it tells us whether to round up or down. In this case, we round up. So we express our answer as 1.67. Now, we wouldn't have to do that to answer this particular problem. This one just asks how many significant figures are appropriate to show in the result. So we would really just have to get to this part where we figured out that this step would have 3 significant figures, which gives us the answer C. But I did want to show you how we would continue and get the correct answer. As we make measurements in the lab, we are interested in finding the accuracy and precision of our measurements. The accuracy is how close your value is to the true or accepted value. To use a bullseye analogy, something with high accuracy would hit very close to the center of the bullseye. The way we would determine accuracy in the lab is with percent error. Precision, on the other hand, is how close your measurements are to one another. In other words, how repeatable is your experiment? Do you get the same value every time? That doesn't mean your value is necessarily correct, just that you are consistent. Figure B shows a bullseye in which the holes are precise but not accurate. They hit in roughly the same place every time, but it was not the center of the bullseye. Precision is determined in the lab using standard deviation. The formula for standard deviation is a way to compare each trial to the average, which is a way to compare the trials to one another. Figure C shows something that is neither precise nor accurate. The holes are not in the center and not near each other. In the lab, if you are doing an experiment that has never been done before, you may not have a true value to compare your results to. Therefore, you could not measure accuracy, but could only measure precision. The more repeatable your experiment, the more likely it is that you have found the true value.